Okay, what I'd like to now do is the daily problem. And the daily problem is an instructive one for our idea of backtracking. Okay, it'll seem like kind of a toy problem, but let's think about it. It says you're given 3 strings of characters, X, Y, and Z, okay, where one is of length n, one is of length m, and one is n plus m. We'll say that Z is a shuffle of X and Y. If you can form Z by interleaving the characters from X and Y in a way that maintains the same left to right ordering of the characters from each string, and it says show that this thing, okay, is a shuffle of chocolate and chips, but this one is not. Does everybody kind of see it? Okay, let's take a look at this. I think I'm going to try to write on the board this time. Let's see what Horace... Oh, wait. Boom. Sorry, stop. Okay, good. Let's try this one. So can we argue, how would we show that that first word, chocoleptes, or whatever that is spelled, is a shuffle of chocolate and chips? Can anybody kind of argue? We claim the first one can be made of chocolate and chips. How do we make chips out of this thing, leaving chocolate? Does anybody have an idea how to do it? Okay. See what we're trying to do? This word over here. How can we delete chips from it to leave chocolate? Okay. Does anybody see how to do it? Yes.
Take the first or second C, and then the second H, and the I, and the P, and the S again.
Okay. So the claim is that if we do that, this C-H-O-C-O-A, chocolate, okay, is that spelled chocolate right? Does everybody agree that if we remove the chips that way, we get chocolate, right? Any questions about that? Now, was that the obvious way to pull off the chips? What would have happened? Why didn't we take this H? There's another H there, right? I know how to spell chips, right? Why couldn't we take chips? Why didn't I take that H? Okay. And there's a good reason why not, yeah? What's left doesn't spell chocolate, right? I guess you get a C. Oh, cocoa. You get cocoa. You don't get chocolate, right? Does everybody see that? So in making that decision of which H to be thinking about, does everybody see you got to look ahead? Okay? This is not a greedy-like thing. Does everybody see that? Okay? And the claim here, okay, let's look at the second one. The claim is that there is no way to shuffle this thing to get chocolate and chips out of this one. Why is that? Can anybody prove to me that there's no way to get chocolate and chips out of it? Yeah? What? P comes after S. So you're saying that chips, I can't have a chips because I've got to have a P before S. Does everybody see that? I think I agree with that, right? So the first one can be shuffled, but recognize that, that there's some subtlety here. Okay? Any questions about it? Okay, the second one can't. Okay? That said, what is the second part of the problem? The second part says, give an efficient dynamic programming problem to tell whether Z is a shuffle of X and Y. Okay? And it says, hint, the value of the dynamic programming matrix should be Boolean, not numeric. Boolean means true or false, right? Okay? How can we do this? Okay? Does everybody see what we want to do? How do we do, what is dynamic programming? Dynamic programming, as I know, is efficiently computing a recurrence relation by storing partial results. Does everybody remember that? If we're going to efficiently compute a recurrence relation by storing partial results, what is the first thing we need? What is it the first thing we need? Yeah? We need a recurrence relation. Does everybody see that? Okay? Now, what do we need before we need a recurrence relation? I'm going to say even so. We need to have a function we want to compute by that recurrence relation. This is the way I think about it, right? So what would be a function that we would want to compute that would tell us the answer to our problem, okay, if we could magically compute it? This is the way that I think about designing dynamic programming problems. Can anybody give me a, yes? You want a function? What do you okay, it's your function. What do you want to name your function? Give me a letter. F, okay? This is F for function, okay? F of, what do we want to call it? I, J, K, is that what you want to call it? Let's just say it because I like, this is maybe being silly now. Let's call it S, T, and let's say Y, just because of what we're going to do. And so what are these three arguments? Did you tell me there were going to be three arguments? It's going to take three strings and do what? Returns true if and only if string S and T shuffle to Y. Does everybody agree that if we could compute this function, we know the answer? Okay. This to me counts as progress. Okay. You may say, well, what's progress? We just restated it. Okay. But now I have something to try to compute a recurrence relation for, right? Does everybody see? I want a function that, given these three things, will return true if and only if this and this shuffle to that. Okay? Any questions? Now, can someone give me a recurrence relation for this? Okay? Okay, now this may be, again, this may be a jump at this point, okay? But let me tell you how I would do it, okay? When I think about a recurrence relation, I think at the end, was that a waving your hand? You want to say something or just?
Yeah, I think I had a solution.
Okay, what is your solution?
So you check if the first letter in either of the two input strings is the same as the shuffle.
Right. Yeah.
And you call the function again with what are removed in those strings.
Okay, so he's saying that if we remember back to the chocolate chips one, it started out with, suppose let's say that our word, we had chocolate chips, and the word started like this. The target word looked like this. He's saying, well, the C started only one of the word. Okay, this C, actually, okay. Let's say what he was saying. The C could either match the start of the chocolate or the start of the chips. Does everybody see that? And he's working from the beginning of the string to the end. I, by convention, prefer to work from the end to the beginning. There's not really a big difference, but recursively, kind of I think of the right side as being what's out there. So let's take his basic idea, but change it where instead of thinking about the first character, we think about the last character. Does everybody see this? If I have two strings, and this was my string S, and this was my string T, and here was my shuffle Y, if this matched this character, if these two matched each other, and this character didn't, the only way we could get that last character for the match was at the end of T. Does everybody agree with that? And then we can shuffle them under what condition? If the remaining strings where we hack these two things off are still shuffleable. Does everybody agree with that? Alternately, what if X was here but not there? Is there a way to shuffle them? Well, there is if we hack this character off this and this character off this, and then ask if there is still a shuffle of what's left, right? If they can shuffle what's left, then we got it, right? And there's one case remaining. What happens if both of those strings end with x? How do we deal with that? Okay, yeah?
If you try both, the first doesn't work, you try the second.
Does everybody agree that if this could be, this is either going to get matched to that or it's going to get matched to that? If it gets matched to this, then what's left after you delete it has to be shuffleable. Or I could match it to that, and then what's left there has to be shuffleable. Does everybody kind of get that? How many people see what the idea here is so far? Okay, you may not yet see the recurrence, but maybe you're seeing a recursive program to do this. Does everybody kind of get that idea? Okay, let me now write the recurrence that I want to write. And it's going to be using this idea with, maybe a little bit of a adjustment. Okay? First of all, if I am specifying I need a language to talk about hacking off the last character of a string. Does everybody see that if I'm going to write this? The way that I would like to specify it is the following. Let's now change this function where instead of the arguments being strings, let's say the arguments are indices. X, you're going to hate me for this, Y and Z. These are lowercase. This was a big fancy thing. Okay? What is my definition of this function going to be? Let's say the strings that I wanted to shuffle were big S, big T into big Z, Z. Okay? What if I say instead that this is going to be arguing, this is going to be true if string big S from 1 to x, the first x characters of string x, plus for t, the first y characters of t, can shuffle to z from 1 to z. Does everybody kind of get this idea now? The way I'm specifying my strings is that they are prefixes of the input, right? And now my arguments are not going to be strings, but character positions in the strings. Does everybody see it? Yes. Now S, T, and V are global arguments. Does everybody see this? These are the strings. These are being passed globally. Okay, maybe call it bad programming practice, but this is now outside the recurrence. Does everybody kind of get that idea? Do people see what my notation is? Now, the arguments to my recurrence are numbers, which is usually kind of, we're kind of used to that. Okay, maybe. Okay, any questions? And what will my recurrence relation look like? Now I'm going to write a recurrence to solve it. I claim that f sub x, y, z is going to be true, is equal to true if, actually maybe just put it, maybe I write it in logic. What if I say if, let's say the first case was that what if I did the following? What if we said that if z sub z, the last character of all, was equal to s sub x and f sub x minus 1 y z. Or z sub z equals t sub y. And f sub x, y minus 1, z minus 1. Okay? Let's try to read this and see if this says exactly what we want it to. Okay? Yes, there is a way to shuffle the first x characters of S and the first y characters of T into the first z characters of big Z if the last character of Z matches the last character of X, and there is a way to shuffle the first x minus 1 characters of S and the first y characters of T into the first z minus 1 characters of big Z. Does everybody agree that's saying exactly what he said? Okay? Or, if the last character of Z matches the last character of T, and there is a way to shuffle the first x characters of S and the first y minus 1 characters of T into the first z minus 1 characters of big Z. Does everybody see that this covers exactly this algorithm here? Ka-ching, 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 ka-ching is exactly the recursive thing that he is saying. Yes?
Sorry, I don't see how it will work if the last character is in both x and y.
Well, if the last character is in both x and y, what is it going to mean? This thing is going to be true if it's an or here, right? When is an or thing true? When one is true or the other is true, right? If there is a way to do it by picking the last character off of S, then it'll be true or something. True or something is true. If there is a way to do it down here, the expression is going to be something or true. Does everybody see that? Something or true is true, right? So we are going to be trying it both ways here, right? And we're returning the logical or to it. Okay? So it's not a problem. If it can be done both ways, that's great, right? You should get credit either way you do it. Okay? Any questions about that? Yes?
Do you want an explicit base case? Or?
Oh, now you're telling me that if this is a recurrence, I need a base case too, right? And you're right, I need a base case. What should be the base case of my recurrence? Okay, yeah? When Z is empty. Okay? So what is that saying? I think what you're saying there is, where did my thing go? What about the base case? Let's put it here. What about my base case being f of 0, 0, 0? Does everybody agree that if I take the first 0 characters of S and the first 0 characters of Y, I can shuffle it into the first 0 characters of Z? Does everybody agree that? So what is this going to be equal to? Does everybody see that the shuffle of an empty string and an empty string into an empty string, can it be done? The answer is true, right? Any questions about that? So I need a basis case. That's certainly true. And I need a recursive formula for computing this. And doesn't this sound like exactly the algorithm that we were talking about? Any questions about this? A question like, I don't get it, I can't read it, can you read me the formula? Something like that would be good. Any questions? Yes?
So any case that doesn't reach 0, 0, 0 will be false?
Any case that doesn't eventually spell things off so that everything is empty is going to be false. Does everybody agree with that?
Is there any chance that if it uses the wrong order, it can't reach 0, 0, 0, or is it always?
Is there any chance that if it uses the wrong order, It can read 0, 0, 0. I guess we need something else, maybe a case that's false, right? What cases are going to be false here? Okay. Yeah. Okay, so these are the cases that are true. I want to claim, I guess, what would be a false case? The truth is, I think that if the strings start out where the size of this equals the size plus this is equal to the size of this, it will never be false. Does everybody agree with that? It will never, eventually, if it gets down to here, it's done. I guess the cases where, certainly if f of x, y, z, where x plus y is not equal to z, that should be false. Does everybody agree that if the strings don't have the right size, then that should be false? But otherwise, if we can always keep peeling back, always finding a way to pair it off until it's empty, then we're done, right? And otherwise we're going to get into a situation where I have a character I want to use and there's no way to do it. Then neither this is not going to be true and that's not going to be true. That's the way this is going to come down to be false. Any questions? Yes? So what is the dynamic programming matrix? Well, the dynamic programming matrix is a matrix. Right now, this is kind of a recursive function, right? If I wanted to evaluate it, how would I evaluate it? I would want to have an array that is f of I by j by k. Does everybody see that? Which is going to tell me true or false, is that prefix realizable, right? Once I have the recurrence, now I'd like to put it into a matrix form, right? Instead of letting you wildly solve this recurrence with a recursive program that might be exponential, right? Any questions here? Okay. Any questions before I can maybe we'll talk a little bit more about it. I got a first question for here. Do I need all of these arguments to my recurrence? Is there anything that is going to be redundant here? Yeah?
You already decided that x plus y equals z, so you only need x and y in the matrix.
So the claim here is that if I know that, obviously, by definition, since it's a shuffle, the size of z has to be equal to x plus y. Does everybody agree with that? So is there any real reason why I need to use z as an argument? I could go and do something like this. And then there is a z here. How do I replace this z, though, now that I get rid of it? Does everybody agree that if I replace z here by x plus y and x plus y and get rid of my z's from here, everything is a little simpler? How many people see what I just did and understand why I could do that? Okay, any questions about that? Yeah?
What if you have Z, which is a shuffle, is followed by a bunch of A's, and only look at the shuffle and then disregard the A's? Z really wouldn't be.
Okay, you're saying that, well, in this problem, I'm going to demand, it looks like by definition of my problem here, I am saying that basically z is equal to the size of n plus m, right? So I'm demanding it be an exact thing. If you change the problem a little bit, you want to say a shuffle with garbage, then that'd be a different problem, and you might need a somewhat different recurrence for it. Okay? Any questions about that? Yes? X and Y and Z are the lengths of the prefixes of the strings. That's exactly right. Okay? Before, when we were talking about passing the whole string in there. But in this case, it's easier to think about it, I claim, as the prefixes of the string length. Okay? Any questions about that? Now for the now for the final question. How fast or slow is this algorithm? Okay. You're saying, wait a second, I don't see any loops. Where is this thing? How is this? What is the time complexity of this algorithm? Yes. Is this as bad as the Fibonacci one? Well, if I did this by recursive calls, then yes, it's got to be probably as bad-ish as the Fibonacci one, or probably even worse, actually. Okay? But what if I did this by storing up my dynamic programming table, which is the way I like to think about it, right? And I process things so that I know that these cells that I'm looking up, the values of f, what am I looking up in my dynamic programming table? These calls to f. I'd really like to build, could I have an array store the values of f? So I could look it up instead of recomputing it, right? What would the size of my array be? Okay, for storing this up, yeah? The length of the first string times the length of the second string. Does everybody see that? So what you're telling me is that the way I should think about this as a table to be stored, what if I now think of f as, instead of being a function to be called, I have an array that goes from 0 to the length of s, from 0 to the length of t, okay? And for all values, x and y, which have to go between 0 and the length of the strings, does everybody see it? If it's a prefix, it can't be bigger than the length of the string. It can't be smaller than 0, right? What if I now, instead of calling this recursively and running into my Fibonacci explosion type problem, what if I have an array that's going to store these values? I know the value of 0, 0 is equal to what? What is the value of f of 0, 0? Do we know that? True. Now, what strings are there that might possibly, what values might I then be able to fill in? Once I know the value for 0, 0, can I safely fill in the value of 0, 1? My claim is that to fill in 0, 1, I'm going to need to know what? Basically, what is f of 0? You know, if it was, I can't have things with negative values here. But my claim is that if I am now looking for the case of 0, 1, I can realize a string where I use one character from s, none from t, if and only if z of 1 is equal to that character. Does everybody see that? So I can now fill in this spot. And I can fill in that spot. Does everybody kind of see that? And once I have that, I can fill in this spot, and this spot, and this spot. Okay? Or I could fill in this spot, this spot. This spot, this spot, this spot. Does everybody kind of get that idea? And if you look at the recurrence, if I fill them up in the right order, I will have the values waiting for me. Okay? To just look that up. Any questions about that? Yes?
When you fill it, will you be starting in the bottom right-hand corner of the matrix?
Well, okay, there's a couple different ways I could fill the order in. Perhaps the easiest way to do it would be, again, I actually think that the easiest way to do it is actually diagonally like this. What does diagonally like that mean? Along this diagonal, what are the strings that we're encountering? These are all the strings that add up to length 4 for z, right? This means that I got 1, 2, 3 characters from this string and none from there. This means I got 2 from the top one and 1 from the side one. Does everybody see that? So if I fill them in diagonally, what I'm really doing is filling in by the length of the target, right? I'm first going to try to see which prefix, the prefix of length 1 of the target. Can I realize that? Which ways can I realize that? Then I'll try the prefix of length 2, then the prefix of length 3, and once I've got to the prefix of length x plus y, then I'm done. Okay? Any questions about that? Okay? Now, what is the time complexity of this algorithm? Okay, again, I can recognize that there may be a level of detail here people are getting a little lost in. Okay? But you have to see enough of these things to see how they go. There's a bunch of moving parts. Once you see how all the moving parts work, everything is fine. What is the time complexity of this algorithm now? Yeah? Is it m times n? The way I think about it, we are ultimately caring about this last box. Okay, that's all that I care about. But to fill that in, I've got to fill in the entire array. There are m times n boxes to fill. How much time does it take to fill each box? Well, let's go to the recurrence. I can't do that in my head. Pull off a character from a string. Look it up in an array. That's constant, right? Pull off a character from a string by looking it up in an array. Constant. Is that equal to that? Constant. Look this value up in the table. Constant. Do the AND of two things. Constant. Right? Look up an element in an array. Look up an element in an array. Test for equality. Look up an element in the array, AND them, and then OR them. Does everybody agree it takes constant work once I have these values in my table? So that tells me there's n times m boxes. Each box will take constant time to fill. This is an n times m algorithm. Any questions about that? Okay. I hear an odd degree of silence, but any questions about that? Yes?
Is that true that in dynamic programming in general, you don't write the base case and you just throw it in your array or structure?
So in general, I need to conceptually have a base case. There's no question, but recurrence is not complete without a base case, right? That there's no question about. Now, how am I going to solve this thing? Recognize that to get the efficient result, I don't want to actually compute it by a recursive call, but instead want to compute it by storing things up in a table so that I have the things when I needed them. That's how I solved the Fibonacci recurrence quickly, right? And that's exactly what I want to do. So I do need a base case. My base cases are going to be things I can put down and fill in that matrix without looking too hard at the strings. And then I'm going to have to go and take a look at my recurrence and say, which values can I solve now, just given the base case? Ka-chunk, ka-chunk. And then, now that I've done that, which are the next ones that I can solve, given that I've solved these so far? Does everybody see that? And I'm going to populate my matrix, constantly populate it, okay, until the whole thing is filled with the values and I can actually fill in the value I care about. Any questions? Yes?
What would the complexity have been if we didn't use the matrix?
If you didn't use the matrix, okay, this is something I can't even dream of. Okay, let's think about what it might be. Okay? In order to solve, let's say the S and M, let's say that both strings, these strings, both of my strings are of length n, right? What is it going to be? Well, this is going to be given by maybe it is something like 2 to the n. Let's just think about it. It is, the way I would think about it is I've got a tree which starts out at nn, and to solve it, call something of length n minus 1, n, and n minus 1. Does everybody kind of see that? The two recursive calls here would be to get to n minus 1 and n minus 1. Does everybody see that? So it would probably be The right way to think of it, I think, is I've got a tree of possibilities that's going to be happening, recursively called, that is going to be of height n, and it's a binary choice at pretty much every position, right? So I think if I don't store it and I run this recursively, I think this is a 2 to the n time algorithm. Okay? But by storing that lousy table, it goes down to n squared, and that's obviously wildly better. Any questions about this? Yes? You know, I don't want to analyze the worst case of this. I want to look at the worst case and say, that's bad, right? And if I can do it without, find an n squared way to do it, n squared is good. Good is better than bad, right? So I don't want to think too hard about bad, about exactly how bad bad is. Bad is clearly bad. Any questions? Okay. But when I think about it, again, how bad, I usually think about what would be the worst case kind of a tree that we would form here. And recognize that, you know, maybe there's parts of it that aren't complete. But any questions? Any questions about this problem? Okay. So I do encourage you to think about, again, we've got more stuff today. Don't start to pack up, okay? But does everybody, I encourage you to think about this as a good example, okay? And maybe a little bit, you know, any questions about that? Okay. Any questions about the chocolate chips problem? Okay. Okay. So what are the 3 steps of dynamic programming? Again, basically you formulate your question, your problem as a recurrence relation, okay? Which means usually define what the function means in English, then write a recurrence relation for it. What is the next thing to do? Show that the number of different instances of my recurrence are bounded by a polynomial. What do I mean by that? Some of you have a homework dealing with backtracking. Am I correct? Backtracking is a recursive algorithm, right? You should be saying, hey, wait a second. I'm now going to think about it. That's a recursive algorithm. Why don't I use dynamic programming and it'll run fast? Okay, there's a good reason. The reason is because the number of different states of that recurrence relation is large. If you do backtracking properly, you will never see any state more than once. Does everybody kind of see it? You're searching through each possibility exactly once. There's no repetition. If they're not going to see something again, does it pay to save it? No. Okay? If, in fact, the number of different answers are not that large, then it pays to save them. Right? And here, the number of answers, every single answer we get on the way of that 2 to the n tree is going to be given by a prefix of the first length of the first string and a prefix length of the second string. The total number of possible interesting calls is only n times m. If you're going to do an exponential amount of stuff, but there's only a small number of different answers, a polynomial number of different answers, then we are in business. Any questions? And the last part is you must specify an evaluation order. How do you fill it in so that the item you have is always there? And if you write a recurrence relation, your recurrence right, it should be clear that that's going to work. Notice that for every one of these to compute this thing, it is calling the recurrence on arguments whose sum is smaller than that. Does everybody see that? If this is x plus y, the calls to the recurrence, the arguments are going to have size smaller than x plus y. Does everybody see that? So long as we compute them in terms of the size of the sum of the arguments, okay, we will have what we need waiting for us if we compute the smaller ones first. Okay? Any questions here? Yes?
How does this dynamic programming solution compare to just doing the naive backtrack and storing each state in like a hash
Okay, so you're saying, why don't I do backtracking for it? Forget this dynamic programming. I'm going to go write the recurrence. Okay? And the answer should be, I should be able to give you strings lousy enough that your recurrence is going to take exponential time.
Yeah, I get the complexity difference between, but I'm asking like if you just, as you're doing the recurrence, you store a state that you're looking at right now in a
Okay, so there is an idea that people sometimes use in dynamic programming called memoization. Okay? Which means instead of actually building this table explicitly, what if you toss the values in a hash table and look to see if they're there before computing something? And if you do that right, that would give you the same thing as the dynamic programming algorithm that I'm doing here. Okay? But I like to think about the table explicitly because it gives me an idea of what the analysis is. And it shows I understand the order of what I'm doing. Okay? So if you're determined to say, no, I don't want to learn about how to use this table, okay, you can go read in other algorithms books about something called memoization. And that's dynamic programming without an explicit table, but something like a hash table. And you can use it on the exams, but I'll take off points. Okay? Any questions about that? But if you find that easier to read about, it's important to know why that. It's reasonable to know why that works.
No,
Okay.
that's how I solved it. I didn't know.
Okay, so that's not a terrible way to solve it. Okay, but I like to think about explicit table. I think that's more pedagogically sound. Yes.
In what way is that worse? I'm just curious.
Well, what way is it worse? Well, what I will say is I can give you a bunch of pedantic answers. One thing I can say is, well, your hash table, you don't know guarantee your hash table is always going to be linear, constant time access, right? Okay, so I can complain about that. I could complain that maybe when you could do this with any kind of recursive thing. You could have done this with the backtracking solution. Okay, and you would have just stored a table of size 2 to the n, and you would have run out of memory before your bandwidth problem finished. Okay, so I think it is important to know when there are problems for which the state space is not large. Okay? So that's, I guess, why I prefer to teach it this way. Okay? There are morally sound reasons for using memoization, but this is how I prefer to teach it. Yes?
How are you making it such that the table fills in that diagonal pattern?
How do I make it fill in like that? Well, the answer is I fill it in like that. Okay? How did you make it? You're thinking to yourself, you guys did that Fibonacci number program, right? F1 to Fn, right? How did you make it fill in like this? Okay? Well, you had a loop that said for I goes from 1 to n. Does everybody see that? And here, how would you make it like that? Well, I would probably say, let's have a loop that goes for z goes from 1 to x plus y. For x goes from 1 to I, and then let the other target be z minus x. Does everybody see that? And then I'm now filling this thing in like that. That's how I would do it. Does everybody see this? The real fill-in order, now that we have to, if you're really going to make me confess it. For z equals 1, 2, big X plus Y, the length of the strings total, right? For X equals 1, 2, or 0 to Z. Then I'm going to set Y equals Z minus X. And now fill in for the case of f of x comma y. This is exactly what it would need to fill it in on those diagonals. Any questions about that? Any questions about this example? Okay? Any questions? Okay. What I'm going to do now, at the risk of getting into trouble, any questions about that? Let me now try what is intended as, again, the way I think you have to understand dynamic programming is to see a lot of different examples. Now, I'm going to try for the first time in my life a new dynamic programming example, which I made in about 10 minutes before I came to class. So I could get into trouble here. That's what I'm warning you. But let me show you a different dynamic programming problem. Although, remember this, because when we get to edit distance, this is going to look a lot like edit distance, what I just showed you over here, this chocolate chips thing. Okay? Let me show you a simpler kind of dynamic. Originally we saw Fibonacci numbers. Yeah, that was simple. I suddenly got into chocolate chips, and this is now looking weird. Let's look at what I think is another form of a dynamic programming problem that maybe is simpler to think about. So let's take a look at it. And it has to do with filling up at gas stations, okay? Does anybody these days for spring break load up the car and drive down to Florida? That's what people used to do, kids used to do. You do that. Okay, good, okay? And so if you drive down to Florida from here, it's 2,000 miles or something like that, you've got to stop and get gas at a lot of places. But you want to get to Florida. It's nice in Florida. You don't want to spend time at gas stations. Does everybody see that? What if we knew, let's try, I'll try over here now. What if we had a world where we were driving from New York to Florida, okay? And we knew where there were gas stations. Okay? And we wanted to plan our gas station trip so that we minimize the amount of time we spend at gas stations. Okay? How can we go about doing this? Does everybody kind of see what the problem is? I want to drive from New York to Florida. I know where the gas stations are. Okay? If I don't know where the gas stations are, I'm potentially in trouble, right? Because I could keep driving and run out of gas and there's no gas, that's the end of the trip, right? Okay, so let's say that I know that I can go R miles on a fill-up. Okay? How can I figure out the minimum number of stops to go between New York and Florida in my car? Any ideas? Yeah?
So we look at the last gas station you have to visit and store it, and then we try, then we look at the previous one before that.
So you want to give a recursive algorithm for doing this, is what I think you're saying, right? You want to look here and say, is there a recurrence relation? If you're thinking dynamic programmingly, what is the argument that I would like to kind of make? Is there a function that I can define that will tell me what the minimum number of stops is? Okay, yeah?
So it's f of this gas station plus f of all the next gas stations.
Okay, so first, how do I do it? I would want to start by writing out an English description of what it is I want to compute, and then come up with a recurrence for it, right? So how would I do it? Let's say G of I is the minimum number of fill-ups I need to get to station I. Does everybody see it? This is gas station G0, G1, G2, G3, G4, ... to Gn. Does everybody see that? What is the minimum number of stops to end up get to Gi? I claim it is one more, the minimum number of stops it takes to get to Gj, plus 1 if the distance between gas station J and gas station I is less than my driving range. Does everybody see it? It doesn't help me that there's one filling station in New Jersey. Okay? If I can't make the trip from New Jersey all the way to Florida on one tank. Does everybody see it? Best I can do is fill my tank up. So does everybody see that this recurrence relation is going to solve my gas problem? Okay, let's read it. Okay? the minimum number of stops it takes to get to gas station I is one more than the minimum number of stops it takes to get to gas station J, okay? Or take it back. So I want to minimize over all possible gas stations J, such that J is before I, and the mileage between the J station and the I station is less than how far I can go on one tank full. Does everybody see that? Any questions about this recurrence? This is one that I want to make sure people understand, this recurrence. Yes? Well, why does it work? First of all, it works. I like to think of things working backwards. Okay? This is how I think of recurrences, as working backwards. Okay? So that's why I'm thinking about it this way. Okay? Any questions here? Okay? Do people agree with this recurrence relation and see how it comes done? This recurrence relation may not look so ghastly as the other one did. Right? We're going to try over all possible arguments or all possible J such that I can take my last hop from gas station J to gas station I. And if so, the minimum number of stops, the fewest number of stops possible to stop to get at gas station I is going to be over all such J. I could do it in the minimum number of ways to get to J plus 1, and I'm going to want to take the minimum of those. Okay? Any questions about this formulation? Okay, how many people think they understand it? Okay, and what's the boundary case? Well, to get to the first gas station, how many stops do I need to make? Well, I'm assuming I'm starting at the first gas station, right? Okay, any questions about it? It's the last place where I got gas. Any questions? Okay, yes? Why wouldn't the greedy algorithm work for this one? What is the greedy algorithm? It means get in your car and drive as far as you can before running out of gas, right? And the answer is the greedy algorithm does work for this. Okay? But you needed a proof of that or an argument of it. Okay? But you're right, the greedy algorithm does work for this. Okay? Does everybody see that the right way to do it might have been to start where you are, drive as far as you can, go to the farthest gas station, okay, and that will work for this. Any questions? But let's stick with the dynamic programming solution a little bit. Yes?
So a problem where you would need to use dynamic parameters if every gas station only had a certain amount of gas to fill up with?
Okay, so now what I want to say is, as you're saying, let's go through what we're saying here. First of all, what's the time complexity of this algorithm? Okay? This gives us, I want to claim an n-squared algorithm. Okay, why is that? I've got how many boxes to fill if there's a total of n stations in the universe? There are n boxes to fill, right? From G0 to Gn, right? How much time will it take to fill? Well, I'm minimizing overall J within driving range, right? If there were if all the stations were within driving range, I might have to look at all values of J from 1 to n. Does everybody see it? That clearly the number of J that I can look at can't be more than n. Okay? On a long trip, it's going to be defined by the range of my tank. So in the long run, unless I'm really driving a tanker, okay, it won't be that many stations. But the way I think about it is, I've got n boxes to fill. I'm minimizing over potentially all J less than I. That means it might take n steps to do it. This would be an n-squared algorithm recursively. Any questions? Okay. Second, as we noticed here, okay, you're now saying, hey, this algorithm isn't so hard. I could do it by greedy algorithm. You could do it by breadth first search. Okay, if you kind of think about it as building a graph where there is a graph between any two stations within driving range. Does everybody see that? If I add an edge between any two stations that you could drive from one to the other, then it would be the smallest number of fewest hops I need to cover to get to where I'm going. Does everybody agree that that would be a breadth first search? How many people agree with, see that? How many people are confused what I'm asking? Okay. Does everybody see another way to think about the greedy algorithm was drive as far as you can before running out of gas. Then fill it up and drive as far as you can without running out of gas. Another way to look at that would be if I put an edge between any two stations within driving distance range of each other, right, whose distance is less than r, and then do a breadth first search from here to there. That would be the smallest number of hops. That would, in fact, do the greedy algorithm. Does everybody agree with that? Okay. Now, this I like the way of thinking about, because, in fact, many dynamic programming algorithms are really shortest path algorithms in disguise. Okay? So that's one thing to be said about it. Yeah?
What is the greedy algorithm for shortest path take n squared to initialize anyways, so...
Would the greediest algorithm for shortest path take n squared? Well, if the graph was full enough, then it's kind of maybe an n squared thing. Both of them, I think, are reasonably efficient. Okay? Any questions? But why do I think dynamic programming is interesting? Let's try some other variants of it. Suppose instead we wanted to minimize the average price of gas that we go to. Okay? So now let's imagine that every gas station has a price per gallon on it. Okay? At this place, it's $3.02 a gallon. Here it is $3.15 a gallon. Here, knowing that there's a bunch of people using the greedy algorithm and there's all those New Yorkers running out of gas over here, here they charge $96 a gallon. Does everybody see that? Okay. Now, suppose we have a price for the gas at each station. Okay? And let's say, and this is not a perfect optimization function, but let's start to think about it. Now, let's say I want to find the way to drive from here to here such that I stop at a certain number of gas stations and the average price of the gas at the stations that I visit is as small as possible. Does everybody kind of see that? If I get stuck doing this, 96, 3, 3 and this would mean I stopped at 96 plus 3 plus 3 divided by 3. That would work out to something like about, what is it? That's 30-something a gallon. Okay? Any questions? Okay? Now, notice my greedy algorithm doesn't look so good for this. Does everybody see that? How can I find which is the right way to buy gas to minimize the per station price? Okay. I claim a recurrence like this starts to be more interesting. Okay, let's let G sub ik be the minimum total gas per gallon price needed to get to the gas station G in exactly k stops. Now I've got two arguments to my recurrence. Does everybody see this? Okay, two arguments to my recurrence. One is what is the gas station that I'm at, and the other is how many stops did it take to get here. Okay? And I'm going to say I want to now know what is the minimum total per gallon price needed to get to this gas station in that many stops. What do I say it is? I say I minimize over all stations within driving range of me, right? It is the cost I claim that the cheapest way to get to gas station I in k stops, okay, is I'm going to have to stop before it at some station J. Does everybody see that? if I stopped, I want to now know what's the total price per gallon that people have paid, getting to J using K minus 1 stops. My last stop is going to be ending up at, okay, let's say I filled it up for the last time at station J. I am going to pay the price of the gas at J. I'm going to add that to the cost of all my fill-ups so far, right? And to end up at K stop fill-ups, basically, I want to know what was the cheapest way to get to J after K minus 1 fill-ups. And to that, I'm going to pay the cost of my last fill-up. How many people understand the recurrence? How many people don't understand the recurrence and have a question? Question like, I don't understand the recurrence would be a good question. Any questions? Anyone? Do you see how this has sort of the same structure as the other recurrence, right? Except now the function's a little different. It's keeping track of not only what was the, instead of telling me how many stops, it's telling me what's the cheapest way to get to. Okay? The cost of the cheapest way to get to station I after K stops. And I can figure that out once I know the cheapest way to get to any other station after K minus 1 stops. Does everybody see that? Any questions about this? Yes?
For the graph algorithm still, if you made the weight the price of the gas station you're going to and you use Dijkstra's algorithm?
Would this be like the weight of the other one if I had it be the weight of the... okay, so you're saying, could I make this like Dijkstra's algorithm? You're saying, give me a graph where the weight of, at any vertex is kind of the cost of stopping there and paying that gas per gallon thing. The answer is that would find the minimum total cost of the gas stations that you stop at. But that doesn't minimize the average cost. If you think about it, you might want to, because the average cost means you have to divide it by the number of gas stations you actually stop at, right? You're just minimizing minimum total path length, as opposed to, a function of how much averaging over that. So it's a little bit of a different question, right? The truth, though, is this is like the Dijkstra's algorithm. Remember we gave you a daily problem where there was a Dijkstra's algorithm. I said, find the shortest path using exactly K edges? Well, that is exactly what I'm doing here, isn't it? Okay? And so in that sense, it is just like the other problem. There is really, if you look deeply enough, dynamic programming problems have a lot to do with shortest paths. That is true. Okay? Any questions about it? Yes? What is MJ? MJ is the mile marker of the gas station. So this gas station, I didn't probably negotiate that, but you're right. I should know here where it is. Palm Beach is at mile marker 2,000, right? But here, the first gas station is 17 miles on the road. The next one was 23 miles down the road. Does everybody see that there's a mile marker on the trip of where the gas station is? That's what I mean by those miles, right? And can I drive between this station and this station? I can if the mile marker from this minus this is less than my driving range. Does everybody agree? Okay. If this thing is a mile marker 550 and my car has a driving range of 500 miles, what's going to happen if I start driving from here and head out to there? Well, 550 minus 46 is going to be 504. What's going to happen is I run out of gas 4 miles out of town, right? Any questions about that? Any questions about these recurrences? Let me give you one more here, because this isn't quite the right argument for pricing gas either. Because it didn't tell me, maybe it's okay for me to stop at that expensive gas station if I don't put too much gas in there, right? What if I want to minimize the total amount of that I pay for gas getting to a certain place? Okay? Let's say that I have to buy my gas in quantities of a gallon. So I'm not going to be able to buy a half gallon. I have to buy a gallon at a time. Okay? What's the cheapest way to fill up the gas thing? What if I let G sub ik now be the cheapest way to get the gas station I, where I end up with k gallons in my tank? Right? How much I have in my tank will tell me how much I can, how far I can drive from here. Now my state is going to be, what station am I at with how much gas in the tank? What is the cheapest, the best possible way to end up at station I with k gas gallons in the tank? My claim is, it is the minimum over all numbers of gallons I'm going to fill up at the amounts of gas I'm going to choose to fill up at this station. First, I'm going to pick what station do I fill it up in. Second, I'm going to have to decide how many gallons will I put in here. Does everybody see that when I go to the gas station? It's a certain price for it. I've got to decide how many gallons I'm going to choose to put in. My claim is, if I'm going to end up at, gas station I with k gallons, how could I do it? Well, the cost is going to be at some previous station. Okay? I got to that station having c gallons in that tank, and then I filled it up with enough gas to get me here leaving k gallons. Does everybody kind of get that idea? Okay. Now, if I keep my state as being both the station and the amount of gallons I need, now I can figure out the cheapest way to end up here. Any questions about that? Okay, this I can think maybe a little bit more detailed than we wanted to go into. But what is the lesson here? The lesson here is that I can put pretty complicated objective functions here and still find what was the right tour with the same basic kind of a framework, right? To find the cheapest way to get to a certain state, so long as it depended upon the cheapest way to get to some other state. Okay, I get a recursive idea. And that recursive idea is what I want to do. Any questions about this? Okay, any questions at all? Okay, don't know if that cleared things up or not. We have 1 minute. Okay, we will talk about this more next class, but let's understand this so I can prove to say I did talk about edit distance. Okay, we're going to be talking about ways of measuring the changes in strings. Let's say I've talked about it, and we'll talk more about it next class. Okay? Thanks for your attention. Think about it, and we'll talk about it next class. Okay, thanks.